explain the concept of resonance. How can we delocalize electrons? For that, we're going to choose the example of the allyl cation. This is structure over here. And this carbon is sp2 hybridized. This is sp2. So carbon number 1 is sp2, carbon number 2 is sp2, carbon number 3 is sp2. To understand how we can move pi electrons, those are pi electrons. Here is a pi bond, here's a sigma bond. How we can delocalize pi electrons, let's do a different drawing. Now I'm going to do this showing the sigma bonds, and I'm going to draw the hydrogens in each carbon as dashes and wedges indicating going inside the plane of the board, let's put it that way, and wedges are coming onto you. So here we can draw the same thing. And so we have two hydrogens here, two hydrogens here, and two hydrogens here. The point is that whenever we have sp2 carbons, we have 3 orbitals in a trigonal planar distribution and a p unhybridized orbital which is perpendicular to the plane of the board. In this drawing, I'm choosing to have the molecule perpendicular to the board, so now I can draw the p unhybridized orbitals in the plane, which are these. So all of those are parallel. If we have these orbitals parallel, we can say that we have the pi bond, which is formed by the lateral overlap of the two unhybridized p orbitals, but we could also say that we can form that pi bond on the other side. That means that those pi electrons are delocalized between carbon 1, 2, and 3. And we can say, make a drawing. What is that? How can we represent that in resonance structure? So we understand that we can move pi electrons as long as the p orbitals are coplanar, so parallel to each other. If we have them the allyl, and now we know the p orbitals are parallel, we can delocalize these electrons over to this side. So and now between carbon 2 and carbon 3, we are going to have a double bond. Now, these two structures are said to be resonant structures of the allyl cation. And neither one of them is a good representation of the real molecule. The real molecule is a hybrid of resonance of these two. And we represent that we can draw partial double bond on the side, partial double bond, and a delta positive, meaning partial positive charge in carbon 1 and partial positive in carbon 3. So we can delocalize pi electrons so long that we have the correct symmetry in the p unhybridized orbitals. Let's do another example of how do we know when can we move electrons and delocalize. Also, delocalization means that this charge is spread, and because of that, those structures is more stable as if the electrons are localized. So resonance implies electron delocalization and stabilization. So lower energy. And that's important. That's a consequence of the resonance. Let's do another example here. We have an amide. And here we have a pair of electrons over the nitrogen and over to the oxygen. And now these two positions in the double bond, this atom and this atom, are said to be vinylic. And the next one is an analytic position. So this is sp2, sp2, sp2. So we assume that we have the correct symmetry. These electrons can be moved, and we can also draw a resonance structure for the amide. And Later we can explain more examples of that. In industrial structure, we will have a formal positive charge on the nitrogen and a formal negative charge in the oxygen. Also, formal charges are very important to decide whether a resonance structure contributes more or less to the resonance hybrid.